Hi, I'm Dr. Gareth Moore from RP Photonics, and welcome to this RP Fiber Power tutorial series. Today I'm going to show you how simple to use, yet powerful, our fiber simulation software is. Let's dive right in with a case study which you can find on our website. In this video, we'll explore a Chirped-pulse amplification system. Here we want to amplify a 5 nanojoule, 100 femtosecond long pulse to at least 5 microjoules, while still maintaining its spectral and temporal pulse shape. The challenge is that high pulse powers can cause significant distortion due to nonlinearities in the fiber. To counteract this, we first stretch the pulse, reducing its peak power. We then amplify it, hopefully with minimal distortion, and recompress it. The result should be a high peak power pulse with the desired shape and duration. Let's see how it's done using RP Fiber Power. For this simulation, we use the power form titled Fiber Amplifier for Ultra-Short Pulses. In the form, we activate the first pulse, set its energy to 50 nanojoules and wavelength to 1030 nanometers as planned. We select a Gaussian temporal pulse shape with a duration of 100 femtoseconds. This is the pre-stretched pulse. To simulate the stretching, we apply a second order dispersion of 3.6 times 10 to the 6 femtoseconds squared. This assumes that we can stretch the pulse without introducing additional nonlinear effects. Next, we set the temporal width and number of amplitudes we simulate, essentially defining the temporal resolution of the simulation. We then proceed to define the amplifier stage. Here, we specify a single mode ytterbium-doped fiber with a relatively large effective mode area. We choose a generic ytterbium-doped germanosilicate fiber and use the show override section to customize its properties. We set the core radius to 16 microns and the laser mode radius to 17.6 microns. This gives us an approximate 100 micron squared mode area. Since we are simulating the fundamental mode, we use a Gaussian shape. We set the pump mode radius to 15 microns and ensure that all the override checkboxes are selected. We define the ytterbium doping density as 10 times 10 to the 24 per cubic meter and set the fiber length to 2 meters. We also add an appropriate chromatic dispersion and the nonlinear index as properties of the fiber. Next, we activate a pump, setting its peak power to 2 watts at 940 nanometers in the backward direction. The initial state of the fiber is set to pumped, meaning that before arrival of the pulse, the amplifier is assumed to have been pumped for a long enough time to reach its steady state. Before we run the simulation, we select the output signal pulse diagrams in both time and wavelength domains, ensuring that we include their phase profiles. We see that our pulse is successfully amplified to over 5 microjoules, reaching an output peak power of around 64 kilowatts. This level of power will induce significant, but hopefully not excessive, nonlinear phase changes near the amplifier's output. Looking at the output diagrams, we can get a better idea of the pulse shape. The pulse duration became significantly reduced from 100 picoseconds in the stretch pulse to only 78 picoseconds. This occurs because the chirp pulse's temporal wings, which correspond to the spectral wings, receive less gain due to the limited gain bandwidth of the fiber. The trailing wing also experiences gain saturation, resulting in a pulse that is shifted forward in time and redshifted in the wavelength domain. Even though we have a large output peak power, the phase changes are still dominated by the pulse stretching. Now we want to recompress our pulse. To do this, we can use our automatic pulse compression feature, where we use, in this case, up to the third order dispersion. We observe that the pulse compression is not perfect, resulting in a pulse duration of 145 femtoseconds. We also see significant pulse shape distortion, particularly in the time domain. When we include fourth order dispersion, the pulse duration improves to 129 femtoseconds. Those side wings remain, which could be problematic in some applications. To understand this, we can turn off the nonlinear effects by removing the nonlinear index from our fiber properties. After compression, we achieve a pulse duration of only 119 femtoseconds, with a much improved pulse shape. This confirms our expectation that the nonlinear phase shift in the amplifier should not exceed a few radians. It's surprising, considering the amplified dispersive phase shifts during the stretching amount to a few thousand radians. But the pulse stretcher applies a parabolic spectral phase shift, which is quite different from the nonlinear phase shifts in the fiber. We need to try a different approach. Our next option is to use a double-clad fiber. We adjust the pump radius to 62.5 microns with a rectangular shape, simulating a pump cladding with 125 microns in diameter. We also increase the fiber length to 10 meters and the pump power to 3.3 watts. These parameters give us enough pump absorption and gain. However, the nonlinear effects remain too strong for this fiber length. While we can amplify the pulse effectively, recompression becomes challenging, resulting in a pulse duration of nearly 200 femtoseconds. Optimizing dispersion up to the 6th order helps, but is quite difficult in practice. The last option is to shorten the fiber and significantly increase the pump power, even though the pump will not be completely absorbed. We find that even with compression using dispersion up to only the 3rd order, this approach works much better than the 10 meter fiber. This way we can trade off the complexity of pulse compression against the required pump power to some extent. I hope you've seen today how easy it is to run through multiple design iterations and strategies with RP fiber power. We've seen that even for active fibers with substantial mode areas and long stretch pulses, nonlinearities substantially affect performance. Managing nonlinear phase changes to only a few radians is essential, despite the much stronger phase change due to pulse stretching. Imagine trying all this with trial and error in the lab. With these simulations, we not only come out with a better amplifier design, but a much stronger understanding of these complex topics. To learn more about what our software can do for you, visit our website and click on the Software tab. For more case studies like these, click on the Case Studies and Tutorial button under the Encyclopedia tab. Thanks for watching, and please feel free to reach out with any questions.